This video goes over the anti-block going down an inclined plane problem. It is the case of a bicyclist climbing a hill and trying to figure out what is the maximum gradient they can climb the hill. You will notice that in solving this problem, we will be able to approach it from principles first and solve top down. In addition, we will not have to spend the time rotating the axes to make sure the acceleration is in one particular direction. Let's get started. In this problem, we are going to be bicycling up a hill. That means we're going to go against the force of the earth. The ground will provide the force of both holding the bicycle up and providing the friction to move the bicycle forward. And in addition, we're going to have some air resistance as the bicyclist climbs. The key here is we will make sure that the bicyclist moves at a constant speed. So for most intro physics, they use the force equals mass times acceleration. This is a vector equation. And in this particular case, since this velocity will be constant, there will be no acceleration. Here's the expression saying this is how we will define our net force. Other videos can show you how to put in subscripts and also arrows. What is the force of the earth? This is a vector in 2 dimensions. It has a magnitude of m times g, and the direction relative to the horizontal axis is minus pi over 2 radians. What is the force of the ground? Well, it has 2 components. First of all, the ground is pushing directly out perpendicular to the interface, but at the same time, through the fact that the tires are pushing against the ground is providing the force to move the bicycle up the hill, and that's the frictional component. The frictional component is again a 2D vector for which the magnitude is that of the force of me, the rider, at the angle of the gradient relative to the x-axis. I can actually measure my force by looking at the power meter that I have and dividing by the speed at which I'm traveling up the hill. The force of the ground is a compression force. It is some value that we don't know. Its angle is theta plus pi over 2 radians. And finally, what is the force of the air? The force of the air, again, is a 2D vector. Its magnitude is some constant times the speed squared. Its angle is, again, theta plus pi radians. So what do you mean by a 2D vector? Well, that's a vector that has a magnitude and direction, and we can break it up by the components, again, by the magnitude times cosine, the angle along the x direction, comma, the magnitude times the sine of the angle, so that we can get the y component. Finally, if you want to point it in, the fact that the acceleration of the bicycle is 0 in both directions. Now we can have Maple write out the force equation. It makes all the substitutions in. We've been able to apply a top-down approach. It's doing all the details. There's the x component, which is equal to 0. There's the y component, which is equal to 0. Traditionally, in an introductory physics course, this will take 40 minutes to produce. It takes far less and is more conceptually understandable. At this point, we now have 2 equations and 2 unknowns. These 2 unknowns is we don't know what the coefficient of the air resistance is, and we don't know what the force of compression of the ground is. Everything else in the problem I can measure on my bicycle. Let's extract out the solution for the coefficient of the drag of the air and simplify given the terms that we have. At this point, we can actually calculate that coefficient for air drag because I can measure on my bicycle what my power is, how fast am I traveling up some known gradient, and of course what my mass with the bicycle is. Once we have that number, we can then apply it to any other gradient and any other speed. For example, we can determine what is the maximum gradient I can do if I'm trying to ride at 20 kilometers per hour. And I can also figure out what is the maximum gradient that I can climb without falling over, which is about 4 kilometers per hour. At this point, we can now plug in some values to determine the constant for the air drag. So into our solution, we'll put a mass of 110 kilograms for the rider and the bicycle. G is 9.8. The power from the power meter reads 180 watts. We're traveling at about a speed of 5 meters per second. And the angle, which is in percent gradient, so that's 2%, is converted to radians. And this gives us a value here. Given our solution, we can go back to the expression for theta and solve, or we go back to our expression for c and solve for the angle theta. This will determine our expression for what is the angle given a particular speed and power on our meter. The next question is, if I know that power and I know the minimum speed, what's the maximum angle can I climb? Putting in the value for this value of c and all the rest of the information, now assuming that the maximum I can put out for sustainable is about 300 watts, we find that I get a gradient, in radians, a gradient of 0.16, and that's about the limit at which I can ride constantly without falling over. What I like about this problem is that it reduces the amount of mathematical minutiae the students are spending time on. They can concentrate on the physics, which is the fact that there are forces involved, and particularly the fact that the force that's pushing the bicycle up the wheel is the reciprocal of the wheel pushing against the ground parallel to the surface. And that's coming from the fact that I'm pushing on the pedals and providing the energy to get us up the hill. In addition, you can go back to this problem and select any gradient. Say you want to travel at your typical wattage. What sort of speeds should you be expecting in going up the hill? Go to the document to see other details related to this problem.